5 minutes, so I'll talk for another 15 minutes before we take a real break. Oh, you know what? I was going to pass out homework, but that would be boring on the video, so I will do that during our next break. So I'll do. Okay. All right, so chapter 29 and 30 is what we're covering today. So first, chapter 29, we're going to talk about induction, magnetic flux, Faraday's law and Lenz's law, and induction and energy transfer. It's like a really strange way to word that since we're already talking about induction. I'll say energy transfer related to induction. All right, so induction, if you remember our current carrying loop in a magnetic field, we learned that will cause torque on the loop, causing the loop to rotate. So in terms of energy transfer, you've got electrical energy transforming into mechanical energy. So that's, let's see, right, that's the motors we have, right? So if we have a loop that's rotated with no current being driven through it, let's say, for example, the turbines on a wind turbine, they spin because the wind spins them, so it's mechanical energy causing rotation. But you put that wire, a loop of wire spinning in a magnetic field, that's going to induce current in the loop. So then you get to take the magnetic or the mechanical energy and it transforms into electrical energy. So it's the reverse. The same mechanism works for the dam at Bonneville. They open up the dam, water flows through these water turbines, and as those spin, that creates electrical energy and hence power. So that's induction for you, and it's the basis of a generator. And the full definition of induction is a process of creating induced current and induced EMF. If we remember, EMF is another word for voltage. So we're going to define those terms with equations in a little bit. Yeah, Liz?
So a motor would be transforming electrical energy into mechanical energy, and then a generator would be mechanical to electrical.
Yeah.
That's how they work together? Like in a car or something?
Yeah. Yeah, so your motor is taking, well, there's a lot of processes there.
Yeah, like very generally.
Very generally, yeah, taking electrical energy and transforming it to mechanical. It's not as complicated for an electric car, since you don't start with fuel and then have to transform the fuel into electrical energy first, the way you have to do with a car, a gas car, I should say. All right, so we're going to do a little bit of conceptual stuff before we get to the equations. So let's say you've got a loop of wire and it's connected to an ammeter, but there's no power source. And if you take a bar magnet and you move it in and out of that loop of wire, your ammeter will detect a current flow. And that's actually kind of opposite to the lab we did last week. The lab we did last week, we put a current flew through our wire and created a magnetic field. Yeah, so this is the opposite. So this also uses the modified right-hand rule, but it's a little bit different because now we're dealing with loops of wire like a solenoid. The curling part is the wire, and your thumb is the magnetic field. So if the wire curls in this direction, well, I guess it's kind of dependent on the situation, so I won't get into it with this picture. But if you push the magnet down in this situation, you'll get a current flowing clockwise, and if you pull the magnet out, you'll get current flowing counterclockwise. And we've got a simplified picture later on where we'll actually parse out what situations create a clockwise and counterclockwise current. So induced current is current flowing due to the presence of a changing magnetic field. So last week we said the force, well, we've said it again this week, but we only get a force on a charge if it's moving. Now it's it's even more so with induced current. You can't just have a B field, it has to be a changing B field in order for you to get an induced current. So in the example we just saw, that magnet has to move. It can't just be near the wire, it actually has to be moving in order for the current to be created. So one way you could do that would be to have the magnet move. So like for a generator, you could have the magnet spinning inside of a loop of wire, or you could have the magnet stationary and spin your wire. The effect is the same, but something has to be moving. Either the wire or the magnet has to move. So what we're considering when we think about whether something is moving, you have to think about basically how is, this kind of leads to magnetic flux, which is very much like electric flux. But for that loop of wire that you have to consider how the magnetic field lines are flowing through that loop. Think of that loop as like a window, and the B field lines have to be changing. The flux has to be changing through that loop. And we'll discuss flux in a second. So besides moving the magnet or moving the wire, another way would be if you had an electromagnet that you could tune, so you can change the B field with some sort of, well, if you had an electromagnet, it would be by changing the current. Okay, so let's define magnetic flux. So we use capital phi sub b to distinguish it from electric flux. The units of flux are new. Now we have a Weber. And a Weber is a Tesla meters squared. Oh, right, and you can write a Weber as W. No, WB. That would be confusing. That'd be like watts. WB. All right, and so our equation for flux looks really similar to our equation for electric flux. So you integrate the magnetic field over a cross-sectional area. And so it's really similar to electric field, except electric flux, we had the Gaussian surface where you had to have a closed surface. Magnetic flux doesn't care. So when we're talking about a loop of wire, you're looking at the cross-sectional area of that wire, and so that wouldn't obviously be a whole surface, it's just a plane, the plane of the wire. So the flux is going to depend on sort of the angle that that wire makes with the B field. So if the B field is coming out of that wire at a 90-degree angle, that's going to maximize your flux. So with the dot product there, by definition, we'd have B sine theta dA, and usually it's B dA sine theta, but since that's our integration term, we typically put that at the end. But that angle would be the angle between a little unit vector we like to call A hat or dA hat, denoting the normal to the surface. So in this case, that dA hat, the normal to the surface, is parallel to our B, so our theta between B and a little dA hat is 0 degrees. Oops, sine, not sine, excuse me. I'm gonna put that in red. Cosine, because we had a dot product, not a cross product. Sine would make all these things go to 0. That would be bad. So when our angle is 0, cosine of 0 is what? 1? Yeah, so your integral then would just be, so it would be B cosine of 0 degrees dA, which would be B dA. So it's simple, and if your B field is constant, so up here, let's assume the B is constant, then you can pull it out of the integral. And what would the integral of dA be? A. So that's a simplification that we can frequently make if B is constant. So that would be the case where your loop is rotating in a constant B field. But if your loop is stationary and the B field is changing, you couldn't do this. But if this is at an angle, let's just look at a case where it's at an angle. So we've got the situation where our loop is at an angle. The B field is coming out of that loop. I'm going to draw my little dA hat to show the normal to the surface. And so that makes an angle, actually it's easier to draw it if I draw it right next to one of these guys. So that's the theta between our dA hat and our magnetic field B. And so in this case, you wouldn't be able to simplify it down very far. You'd still have your integral B cosine theta dA. If B was constant, then you could pull B out of the integral, but you'd still have something kind of yucky to deal with in there. And then, of course, our favorite situation if that was how our wire was oriented, what would the flux be? 0, yeah. So in this case, theta equals 90 degrees. So flux of the integral of B cosine 90 dA. The cosine 90 term is 0, so your flux equals 0. So if we had a constant B field and this loop was rotating in that B field, there's going to be points in time where it's maximized, points in time where it's smaller, and points in time where it's 0. If you plotted that on a curve, just this isn't on the test or anything. I'm just trying to see if you guys can think about what it would look like. What would the shape of the flux be as a function of time if it was rotating?
Sinusoid. Yeah.
Exactly. So it would vary with, yeah, so sinusoid, exactly. Okay, where are we at for time? Now, actually a good place to take a break. Chris, do you mind stopping the video again? Thank you.